Welcome back to the deep dive. Today we are going to really dismantle a piece of logic that feels so intuitively true. It basically drives how we make decisions in almost every part of our lives. I'm talking about the logic of momentum.
It's such a powerful mental shortcut. We see it everywhere.
Exactly. I mean, think about it. If you have a leak in your roof and that drip is getting faster, you assume it's going to keep getting worse.
Till the ceiling collapses, yeah.
Right. Or if a stop is plummeting today, you assume it's going to keep crashing tomorrow. We look at the immediate past to predict the immediate future.
Which, in a lot of areas like physics or maybe finance, that's often a pretty safe bet. Objects in motion tend to stay in motion.
But today we are talking about biology. Specifically, we're looking at the eyes of children, we're diving into pediatric myopia or nearsightedness, and for decades, the absolute holy grail for eye doctors has been this idea of the fast progressor.
The fast progressor. It sounds like a character from an action movie.
It does.
But it's actually a clinical classification.
Yeah.
The whole idea is that there's this specific type of patient whose vision just tanks so quickly that we have to intervene with the heavy artillery, and right away.
And that logic seems to hold up, right? If you see a kid whose vision got way worse last year, you assume they are on a runaway train.
That's the assumption, that they're
Wow.
going to get way worse next year.
Mm.
But we have a brand new study here. It was published just last month, January 2026, in Investigative Ophthalmology and Visual Science.
Okay.
It comes from the Pediatric Eye Disease Investigator Group, which is a real heavy hitter in this space. And this study, it basically takes that whole momentum logic, crumples it up, and throws it in the trash.
Sounds like a total paradigm shift. The paper's title is, Does Past Myopia Progression Predict Future Progression? And I guess, spoiler alert for everyone listening, the answer is a resounding no.
It really is. And this isn't just some academic trivia. This changes how doctors should treat patients, and it changes what parents should be worried about.
So, our mission today is to unpack why our intuition is so wrong here. We're going to look at why the fast progressor might just be a statistical ghost, and why, if you are a parent or a clinician waiting a year to see how fast a child's eyes are changing, might actually be the single biggest mistake you can make.
It's a classic case of how monitoring can actually be a form of neglect if the data you're waiting for doesn't mean what you think it means.
Okay, so let's set the stage with the problem that researchers and doctors are facing. We are seeing an absolute explosion in myopia globally.
It's an epidemic, no question.
But the tricky thing is, not every kid progresses at the same rate. Some kids kind of drift slowly into needing glasses. Others seem to sprint toward these really high prescriptions.
And that variability, it's a nightmare for clinical trials.
Yeah.
I mean, imagine you're a company trying to test a new drug to slow down myopia. You want to prove your drug works.
Right.
To do that, you need to show a big difference between the kids taking the drug and the kids on a placebo.
Yeah, if the kids in the placebo group, the ones doing nothing, if their eyes don't get worse, you have nothing to measure your drug against. You can't prove you stopped a car if the car was already parked.
Exactly. So researchers use what's called an enrichment strategy. It sounds fancy, but it's basically just a way to stack the deck in their favor.
Okay, how so?
You try to recruit only the fast progressors. You look at a kid's history and say, okay, you lost a lot of vision last year, so we predict you're going to lose a lot this year. You are perfect for our trial.
So it's about efficiency. You pick the kids who are already crashing, so your drug looks like a hero if it can just stop the crash.
And you need fewer kids, less money, less time to prove your point. That's the theory, but it all hinges on one massive assumption.
That the past predicts the future.
That the kid who was fast last year will be fast this year.
And that's the exact assumption this study decided to stress test. So walk us through the setup. This wasn't a fresh trial, right? They didn't recruit new kids.
No, this was what's called a post hoc analysis. They went back into the data vault, really. They took a high-quality trial called the MTS1 study and just reanalyzed everyone in it.
How many kids were we talking about?
136 children, aged 5 to 12.
And what were they tracking? Because just saying bad vision is a little vague.
They looked at the two gold standards. First, the SER, or spherical equivalent refractive error.
That's the number on your glasses prescription.
That's it. The -2, -3, etc. It tells us how the light is focusing. But they also looked at the structural measure. Axial length. This is the actual physical length of the eyeball, from front to back, measured in millimeters.
And why is that one so important?
Because that's where the disease is. Myopia is almost always caused by the eye growing too long. And the longer the eye, the more stretched the retina is. And that's what leads to the scary stuff down the line.
Retinal detachments, maculopathy, things like that.
Exactly. So knowing the length is knowing the real physical risk.
Okay, so they have these 136 kids, and the premise was simple. Look at how much their eyes changed in year 1,
From month 0 to 12.
and then see how much they changed in year 2.
From month 12 to 24. And just see if the lines match up. If the theory holds, the kids with big jumps in year 1 should have big jumps in year 2.
Before we get to the results, there's a nerdy little detail in the source about the drug they used in the original trial. Something about 0.01% atropine.
Right, and this is actually really helpful for us. In that original MTS1 study, they found that 0.01% atropine. It didn't really work any better than a placebo. It was a wash.
Which sounds like a failure for that drug trial.
For the drug, yes. But for this analysis, it's a gold mine. Because the drug didn't skew the results, the researchers could just pool all the kids together, placebo and treatment groups, and look at them as one big natural cohort.
So it gives us a clean look at how these eyes just behave over 2 years. Okay, let's get to the numbers. Because I think if you polled 100 eye doctors, 99 of them would have bet on momentum. If I have a kid and his prescription jumps by 0.50 diopters in a year, which is a big jump,
Yeah.
he has to be high risk for next year, right?
You would lose that bet. And honestly, you'd lose it badly.
Hit me with the stats.
So the researchers calculated something called a positive predictive value. Basically, if a child is a fast progressor in year 1, what's the chance they'll be a fast progressor again in year 2?
Okay, and the number?
42%.
42. That's less than a coin flip.
It is literally worse than random chance.
Wow.
If your vision got worse by at least half a diopter in the first year, there was only a 42% chance it would happen again in the second year.
So let me get this straight. If I see a kid whose eyes are getting worse rapidly and I tell the parents we need to act now because he's a fast progressor, I'm statistically more likely to be wrong than right.
About his future trajectory, yes. Based on this data, you're making a prediction that fails 58% of the time.
That is just wild.
And it gets even more stark when you look at the correlation. In stats, we look for how tightly two things are linked. Does X move Y?
Like height and shoe size, they track together.
Exactly. Here, the relationship was described as very weak. They found that for every extra 1.00 diopter of progression in year 1, which is a massive life-altering jump,
Huge jump.
it only predicted a smortune 0 diopter increase in year 2.
Wait, hold on. So if one kid is stable and another gets worse by a whole diopter, the difference in their prediction for the next year is only 0.2.
Exactly. It's almost negligible. A massive spike in year 1 barely moves the needle for the year 2 prediction. The signal is just incredibly weak.
The study has a scatter plot, right? I love a good scatter plot.
It does. And if the fast progressor theory were true, you'd see a nice, neat diagonal line going up. Fast leads to fast.
I'm instead.
It looks like a cloud or a shotgun blast, just dots everywhere. Knowing where a dot is on the year 1 axis gives you almost no clue where it's going to land on the year 2 axis.
Was this just for the prescription, though? Because prescriptions can be a bit subjective. What about the hard data, the axial length, the physical growth?
Same story. The positive predictive value for the eye growing more than 0.25 millimeters, the cutoff for fast growth was just 46%.
Still basically a coin toss.
Yep. Whether you look at the function, which is the glasses, or the anatomy, the eye length, the past just did not predict the future.
This feels like it breaks a fundamental law of pathology or something. Usually aggressive diseases stay aggressive. Why is myopia different?
There are two main factors here. One is statistical and one is biological.
Okay, let's start with the stats.
It's a concept called regression to the mean.
I feel like I learned this in college and promptly forgot it. Unpack that for us.
Think of it like this. Any measurement we take has a true value, plus some random noise. Maybe the child had a growth spurt that month. Maybe there was a tiny measurement error. Maybe they were just having a bad eye day.
Okay, there's variability.
So if you specifically select the kids with the most extreme values, the fastest progressors, you are, by definition, selecting the group that probably had the most random noise, pushing them in that direction. You're picking the outliers.
So purely by probability, their next measurement is likely to be less extreme. It falls back toward the average.
It regresses to the mean, exactly. The kids who look like runaway trains in year 1 often slow down naturally in year 2, just because the random noise settled down.
And did the opposite happen with the slow kids?
It did, and this is crucial. The kids who were slow progressors in year 1, the ones you might have said, oh, they're fine, we don't need to treat them, They tended to speed up in year 2.
So the labels just flip-flop. The fast kids slow down, the slow kids speed up.
It's a statistical mirage. But then you layer on the biology. The study points out a very simple fact we often forget. Kids get older.
And growth slows down with age.
Right. Myopia progression isn't a straight line forever. It's a curve that flattens out. The study observed about a 22% slowing in the rate of eye growth in year 2 compared to year 1, just across the board.
Simply because they had another birthday.
Yes. Biology hits the brakes. So think about the trap here. You identify a fast progressor in year 1. You panic. But statistically, they're likely to regress to the mean, and biologically, they are naturally slowing down anyway.
You're predicting a sprint right when the runner is deciding to start jogging.
That's a perfect analogy. The label fast progressor is almost obsolete the moment you give it.
I want to play devil's advocate for a second. This data is from the last few years. We just lived through a global pandemic. Kids were stuck inside, on screens. Did COVID mess up the data?
That's a valid question.
Yeah.
The researchers are very transparent about this. About 20% of the participants had missing data at that 12-month mark.
Because they couldn't get to the clinic during lockdowns.
Right. You can't measure an eyeball over Zoom.
Not yet, anyway.
Let's hope not. But the authors analyzed this. They concluded that data was missing at random. It wasn't like only the kids with bad eyes stayed home, so they're confident it doesn't change the conclusion.
And what about the technology? Could bad tools explain the lack of correlation?
Another great point. Older studies used ultrasound, where you actually touch the eye.
Squishy, uncomfortable, yeah.
And it can be a bit finicky. But this study used optical biometry. Lasers. It's incredibly precise. So the fact they still found no correlation tells us this isn't a measurement error. The chaos is real.
Okay, so the crystal ball is broken. So what? What does this mean for people listening? Let's start with the scientists.
For researchers, the message is blunt. Stop using enrichment strategies.
Stop trying to cherry-pick the fast kids to save money.
Because it doesn't work. This study shows that following kids for a year before the trial adds massive cost and delay. And in the end, you don't even get the group you were looking for.
You're spending millions to find a group that vanishes as soon as you find them.
Exactly. It's a waste of resources.
But I think the bigger impact is for the families and the clinicians. I've heard doctors say this exact phrase, let's just monitor for a year. If he progresses fast, then we'll treat.
And this study suggests that advice is, well, it's potentially dangerous.
Dangerous is a strong word.
It suggests that wait and see is a trap.
Why?
Because of opportunity cost. If you wait a year to see if a child is a fast progressor, two things happen. One, as we've just learned, that label is useless for predicting the next year anyway. You gain zero reliable information.
You're no smarter a year later.
And two, you lost a year. That is 12 months where the eye was stretching. And you can't reverse that. You can't shrink the eye back. That structural damage accrues with every millimeter of growth.
That's a heavy realization. The year you spent gathering data was actually a year of permanent, irreversible pathology.
Yes. If you have a child with myopia, you treat the child with myopia. You don't wait to see if they become a super myopia first.
It really challenges our desire to categorize patients, to put them in these neat little boxes, high risk, low risk.
But the data says those boxes are fluid. A child might be fast one year, slow the next. If you rely on last year's speed, you are constantly reacting to the past instead of treating the present.
So there's really no such thing as a fast progressor type of patient. There is just a patient who happened to progress fast recently.
That's the distinction. It's a temporary state, not a permanent trait.
This raises a massive question about risk. If we can't look at the chart and say, aha, based on this trajectory, we need to act, are we just flying blind?
In a sense, yes, and that's uncomfortable. But this study forces us to be humble. It says individual progression is noisy and unpredictable.
Which brings us to the default action.
Right. If you can't predict who will get worse, you have to assume anyone could get worse.
It democratizes the risk. You can't say, oh, you only changed a little bit last year, you're safe.
No. Remember that scatter plot? Some of the kids who were slow in year 1 jumped significantly in year 2. If you'd used the wait-and-see approach on them, you would have told the parents you're fine, and you would have been blindsided.
That's the nightmare scenario. False assurance based on bad logic.
Exactly.
So, let's wrap this up. We looked at a brand new 2026 study. They asked if the speed of vision change in year 1 could tell us anything about year 2.
And the answer was a clear no. Past progression is a poor predictor.
We learned this is due to regression to the mean, and the simple fact that kids' eye growth naturally slows down as they get older.
And the big takeaway is to stop waiting. Stop trying to label kids before you treat them. The labels just don't stick.
It's a powerful reminder that biology doesn't always follow straight lines.
Sometimes the graph is just a cloud.
Here's a final thought for you to chew on, though. We've established that past rate of change doesn't predict the future. The paper also mentions that other studies found that things like race, gender, and even a child's current age have very limited predictive power for that individual child.
Right. We know those things matter for huge populations, but for the one kid in front of you, they aren't reliable enough to bet their eyesight on.
So, if we know genetics and environment play a role, but we literally cannot predict progression from the clinical data in front of us, does this mean we should be treating every single myopic child as a high-risk case by default? Are we moving toward a world where monitoring without treatment is considered malpractice?
That's the provocative question, isn't it? If you can't rule out the risk, do you have to assume it's always there? If every child might be a fast progressor next year, don't you have to protect them all?
Something to think about. Thanks for listening to The Deep Dive. We'll see you next time.